go to the next question. Okay, so let's read this next question. So a rescue plane wants to drop supplies to an isolated mountain climber, a rocky ridge 235 meters below. So we're in a plane and we're trying to send supplies to someone 235 meters below. Assume the plane is traveling horizontally with a speed 210 kilometers per hour or 58.3 meters per second. So I'll just draw a diagram to represent what we know. So we have a plane. So this is the plane. And we have some person over here. So this is not scale, obviously. Let's say this is the center point of the plane. And we have this person, the center point, or the point where he is at, is right there. Okay, and we're going at a speed of 235. Oh, sorry, 58.3 meters per second. And we're at a height 235 meters. And we're asked to find in the first part of the question, so I'll just go part by part, how far in advance of the recipient's horizontal distance. So we're trying to find, if we were to draw this down, and if we were to draw the horizontal distance, and let's call this x, we're trying to find what this is. How far in advance of the recipients must the goods be dropped so it can get to that person? So this is a kinematics question, and we need to use the kinematics equations to solve for this question. So some values that we're given is the height and the speed. So the first kinematic equation we should use is delta D equals VI, so the initial velocity times time plus a half acceleration t squared. We know that gravity is acceleration and it's pointing down. So let's define a coordinate system. So this will help us. I'll just say positive x in this direction and positive y in this direction. And we know gravity is 9.8 meters per second. So we're going to use this equation to solve for time. The main reason we're doing this is in the horizontal direction, it's traveling at a constant velocity. So the kinematic equations only apply when there's an acceleration. So when there's constant velocity, the acceleration is 0. So we can, when the acceleration is 0, we can just say velocity is distance over time. But in the y direction, we know that the acceleration is due to the force of gravity, which is 9.8 meters per second squared. So we got to use the kinematic equations. So delta D, so from the plane to the ground, is negative 235 meters. So the main reason we use a negative sign here, so the negative sign is important because it'll kind of mess up the value if we don't put it incorrectly. So we look at the final location and where we're starting from. So the final is 0, and we're at 235 meters, and the package is going to land at 0. So final minus initial will give us delta t. So 0 minus 235 is just negative 235. And then vi, so the initial velocity when we drop it is just 0. And we have time, and plus a half. Acceleration is negative 9.8 meters per second squared. So because acceleration is pointing down, we put a negative sign. The package is going down, so the change in distance is negative. It's going downward. And t squared. So here we just have to solve for time. The reason we want to solve for time is because we know we can plug it into this equation, and we already know the velocity here because it's given as 58.3 meters. And we can solve for d, which is just x in this scenario. So we have negative 235 equals, so a half times negative 9.8 is just negative 4.9 t squared. The negative signs cancel out, and we're left with t equals square root 235 divided by 4.9. And then this will give us, so we do the square root of 235 divided by 4.9, 6.925 seconds for an S. Okay, so we figured out the time it would take when we drop the package till it gets to the person. Now we're going to use this value because we know it's the same for the X and Y direction, because the package will get to that person in the X direction and Y direction at the same time. So we know V is d over T. D in this scenario is X, and here, let me write that again. So we know V is 58.3. It was given in our question. D is X, and T is 6.925. Solving for X, we have 58.3 times 6.925. That'll give us 403.7 meters. So that's answering part A. So this is part A. Let's look at part B now. Suppose instead that the plane releases the supplies a horizontal distance of 425 meters in advance of the mountain climbers. What vertical velocity, up or down, should the supplies be given so that they arrive precisely at the climber's position? So we can see we're dropping it 425 meters away in the scenario in B. So for it to get to the climber at the scenario in A, we have to be 403 meters. So if we dropped it earlier, 425 meters away, we need to figure out what initial velocity should we be starting out at. And we kind of think about this conceptually. So if we're further, that means our initial velocity should be upward. So we need to throw the package a little bit upward for it to land at that person because we're a little bit further away. If we dropped it at the same spot, that means it's not going to reach the person. It's going to land like a little ahead of that person. So let's just go through the equations. So we're going to use the same kinematic equation. So delta D is VI times T plus a half AT squared. So we know delta D from before is 235. VI in this scenario is the unknown, so it's not 0 anymore. We're trying to solve for VI. The time in this scenario is something we'll also have to solve for. So in order to solve for this, we have to use this equation over here because we're given the distance. We're given the X value in the question B, which is 425. We're not given time, but we know the initial velocity. So let's solve for time. So time, or let's write the equation out first. So V is d over T. T would equal d over V. So D is X, and X in part B is 425, and the velocity is 58.3. That means T equals 425 divided by 58.3, 7.29 seconds. So we plug that in over here, 7.29, and then make some room over here. And we have plus a half. Acceleration is negative 9.8 times 7.2. Just give me a second here. So 7.29 squared. Okay, so now all we have to do is solve for the initial velocity. So we know that negative 235 equals 7.29 VI. And then we have half times negative 9.8 times 7.29 squared. That gives us negative 260.4. That means negative 235 plus 260.4 divided by 7.29 equals VI. So this is just algebra that we did. We took the 260 to the other side, and then we divided by 7.29 to isolate for VI. So VI equals, plug this into our calculator and we'll get 3.48. So this is positive, that means it will be in the upward direction. So the answer is 3.48 meters per second in the upward direction. That's kind of what we expected it to be when we were trying to conceptually think about what we had to do if we were 425 meters away. Finally, part C of this question asks us, with what speed do the supplies land in the latter case? So in the case of B, what speed do the supplies land? So we have to solve for VF, the final speed. We'll use the kinematic equation. VF squared is VI squared plus 2A times delta D. So this is just another kinematic equation. So it's very useful to memorize the 4 or 5 kinematic equations. So we'll substitute in the values we know. So VF is unknown. VI is what we calculated in the previous question, so it's 3.48 squared plus 2 times the acceleration, negative 9.8, times the distance, which is given in the equation, given in the question as negative 235. So that's just the height. So we're using the kinematic equation in the y direction because that's where the acceleration happens. We would not use kinematic equations once again in the x direction because there's no acceleration in the x direction. So we'll just solve for VF squared. This will give us, so 3.48 squared plus 2 times negative 9.8 times negative 235. 4,618 VF. So we'll take the square root. And that'll give us 67.96 meters per second. So that's the final velocity that the supplies reach when it reaches the climber person. So let's look at the attempted solution by the student. So they use the correct kinematic equation and they solve for t, and they plug it back in to the v equals d over t to get 404 meters. Let's just double check what we got up here. So we got 403.7. So this is probably just rounding error based on how many decimal places we kept. For part B, since it needs to be further distance, okay. So they find the time. We got 7.29, so that's correct. So we have 7.29 over here, and then they use the correct kinematic equation to solve, and they get 3.48. So they get the right initial velocity, and then for part C, so 3.48. Finally, they use the right kinematic equation to get the correct answer of 67.96 meters per second. So solution is correct. Great job. Okay, let's get on to the next question.